This is our second video on light waves, and in this video we will continue working with the problems related to the Snell's law. And on the left side picture and on the right side picture you see the thin film interference. I also wanted to talk a few words about coherent and incoherent light. So the coherent light is a light in which the photons are all in step. In other words, the change of the phase within the beam occurs for all the photons at the same time. So the light on the left top in pink or red, you see coherent light, and at the bottom, blue or purple, you see incoherent light. And also on the right side picture, you see that there is laser light, it's coherent light, and incoherent would be the LED light, because the light just produces certain color, but they are not like LEDs. They can be different colors, but they are not coherent light. And laser light, because it is in all the waves are coherent at the same phase, they have stronger and they carry stronger energy, or they're stronger than the incoherent light. So incoherent sources emit light with frequent and random changes in phases between the photons. An interesting fact is that you can make a normal light a source of a coherent one by making it smaller. In other words, like reducing the number of atoms that it may emit, or quanta, the photons. But if we do this, the intensity of the light decreases. The creation of electromagnetic waves begins with a charged particle. This charged particle creates an electric field. You see the electric field picture and magnetic field perpendicular to it. When it creates, as a part of oscillatory motion, the charged particle creates ripples or oscillations and in its electric field, and it also produces the magnetic field when electric field is changing. So electromagnetic waves are self-propagating transverse waves. And if you remember transverse waves from AP Physics 1, these are the waves that travel, the particles travel perpendicular to the motion of the wave, and the wave itself is not traveling, it's the energy that is traveling, transferred from particle to particle. And so transverse waves, particles are perpendicular, their motion perpendicular to the motion of the wave, and longitudinal waves, their motion is along the motion of the wave. So if you compress the spring will start oscillating back and forth. So this is longitudinal wave. And sound waves would be a longitudinal wave, because when we're speaking, our throat produces the vibration of the air around us, and the waves that are traveling, the particles are moving the energy from one to another, and it's longitudinally along the motion of the wave. But in transverse wave, it's like a rope when you shake it, and every particle of the rope is going up and down when the wave is traveling forward. So particles are traveling perpendicular to the motion of the wave. So electromagnetic waves are self-propagating transverse waves of oscillating electric and magnetic fields. And the direction of the electric field is indicated by the purple picture right here, color, and the magnetic field is in blue color. And if you're interested in more mathematical explanation of the electromagnetic waves, I would suggest for you to look up for Maxwell's equations. But I just wanted to mention for you this part of the electromagnetic waves, that they consist of electric and magnetic waves perpendicular to each other, because I wanted to talk about the polarization of the light. So the transverse nature of the electromagnetic wave is quite different from any type of other waves that we have discussed in the past. So unlike usual rope wave, the transverse wave, the electric and magnetic vibrations of an electromagnetic wave occur in numerous planes. And a light wave that is vibrating in more than one plane is referred to be unpolarized light. So the light emitted by the sun, or by a lamp in a classroom, or by a candle flame, is unpolarized light. Such light waves are created by electric charges that vibrate in a variety of different directions, and the creation of electromagnetic wave that vibrates in a variety of different directions as well. This concept of unpolarized light is rather difficult to visualize. In general, it is helpful to picture unpolarized light as a wave that has an average of half its vibration in a horizontal plane and half of its vibration in the vertical plane. So it is possible to transform unpolarized light into polarized light. So polarized light waves are light waves in which the vibration occurs in a single plane. The process of transforming unpolarized light into polarized light is known as polarization, and there are a variety of methods of polarizing the light. And some of the methods of polarization are polarization by transmission, by reflection, by refraction, and scattering. And the most popular way of polarizing light is using a Polaroid filter. And Polaroid filters are made of a specific material that is capable of blocking one of the two planes of vibrating of an electromagnetic wave. So when unpolarized light is transmitted through a polarized filter, it emerges with one half of intensity of its initial intensity and with vibrations of a single plane, and it emerges as a polarized light. And this is what you see here in the picture. The light that is coming, it's unpolarized, and actually the one that is coming, it's not only just like this in one plane, it also spins. So when it comes through the polarizer, it's like little scratches on the surface, and when it comes out, it is polarized. It's just in one plane. So this is why they use polarized glasses, because these glasses take away the intensity of the light and it does not cause as much damage to your eye. And also they use polarized covers for different like lenses, and even the phone for not having reflection. And this is why you can see through the lake with your polarized glasses too, because you only see one plane of the wave and everything else is blocked. So you don't see the reflection of the light of the lake. You see deeper into the lake with your polarized glasses. In the previous video, we also talked about Snell's law and refraction, or index of refraction, and it happens because the light travels from one medium to another medium, but it also happens in the same medium. So let's say you may sometimes see, like, if the ship is in the sky, and that happens because the colder air drops and the warmer air rises. So the warmer air is rarer medium or thinner medium, and the colder air is denser medium. So because they have different density on the top and the bottom, the light that is reflecting from the ship actually bends and comes from the direction, like the dotted line. And so when your eye sees it coming from this direction, your eye thinks that it's actually coming from over here. So this is why sometimes the mirages appear when it's a hot day. So it looks like there is water when there is no water, because how the sky is reflected and looks at the ground like if it was there, if there was something. Another cool effect of refraction and the different density of the air on the top and the bottom is when you see the sunset or the sunrise before you actually see the sun. And that happens also because it's past the curvature of the earth. You would not supposed to be wherever it is, like in this case it's a ship. You would not supposed to be able to see that ship, but you do see the ship because of how the light refracts and comes from the direction where there is no ship, but it appears that there is a ship. And without the light refraction, you would not be able to see that ship behind the horizon. And here is one more very interesting example of light refraction. When the light comes from space and enters atmosphere, it goes from no density, or there's no medium, to medium. It also refracts because of the medium. So when your eye catches the light that is coming from the object that is far away in space, it appears to be higher than the object is actually is. So you see right here, it's a perceived position of the object and the true position of the object. So when you look at the sky, you also do not see the objects where, not that you only see the objects that some of them already light travels millions of years or thousands of years, but you also do not see them where they're supposed to be because of the light refraction when the rays enter the atmosphere. So we did cover Snell's law in the previous video at the end, and we did a few questions only, didn't get the chance to do a lot of video questions related to Snell's law, but let's look at a few more questions and solve them together. So in this question, they say light of wavelengths 589 nanometers in vacuum passes through a piece of fused quartz of index of refraction and given 1.458. Find the speed of light in fused quartz, and then what is the wavelength of the light in the fused quartz, and then what is the frequency of the light in the fused quartz. So the definition of index of refraction is the speed of light in the vacuum over the speed in the medium. So from here I can find the speed of the medium is equal to the speed of the light over the index of refraction. So that is 310 to the 8 meters per second divided by 1.458, and that is equal to 2.058 meters per second. So that is the speed of the light in the fused quartz. What is the wavelength of this light in the fused quartz? I'm going to use the same equation, but the little trick that I know about the frequency. So n is equal to the speed of light, that is the frequency, times the wavelength in vacuum. So I'm going to write it sub-zero. And the other one is the frequency times the wavelength in the medium. So let's call it 1, and let's call this one also 1. And the frequency can be cancelled. So lambda in the vacuum over lambda in the medium is equal to n. So there's another formula that I could use, that n is also equal to lambda in the vacuum, wavelength in the vacuum, over the wavelength in the medium. And they give me that wavelength. So from here I can say that the wavelength in the medium is equal to the wavelength in the vacuum over n. So that is 589 nana, means 10 to the negative 9, divided by n, which is 1.458. So that gives me the wavelength in this medium, or the fused quartz is going to be equal to 403.98 nanometers. And then they ask you what is the frequency of the light in the fused quartz. So the velocity is 1, I'm going to call velocity in the quartz, is equal to the frequency in the quartz times the wavelength in the quartz. But the frequency is the same in the vacuum or in the medium, so it doesn't matter. And this frequency is going to be equal to the velocity over the wavelength. So the velocity is 2.058. It was 10 to the 8. I forgot here 10 to the 8 in our problem. 10 to the 8 meters per second. Okay, so that is our velocity, 10 to the 8. And divided by the wavelength that we just found, and that is 403.98 nano 10 to the negative 9. And that gives me the frequency is equal to 509.34 10 to the 12 hertz. In this question, they say, suppose the ray in the air with index of refraction equals to 1 enters a slab with index of refraction N2 is equal to 2.5 at 45 degrees angle. So incident angle is 45 degrees with respect to the normal. Then exits the bottom of the slab into the water with water index of refraction 1.33. At what angle to the normal does the ray leave the slab, which is theta 3 that they're asking you? So in this question, I'm gonna do again Snell's law. So I can rewrite Snell's law this way. So the angle of incidence is equal to, so this is the first angle of incidence. This is the angle of refraction, but it also angle of incidence. So this angle is the same as this angle. It becomes an incident angle, and this becomes the refracted angle. So because this is equal to that, and this is equal to this, I can say that N1 sine theta 1 is equal to N3 sine theta 3. And now if I plug in my numbers, I will get 32 degrees for an angle of refraction for angle 3. So you see I plug in the numbers for N1 and N3. And N1 and theta 1 is given 45 degrees. And then I solved for sine theta 3, and then I used the inverse sine function to solve for the angle. So I did show you this and mention this in the previous video, that thin film interference is a natural phenomenon, and that it occurs when light waves reflecting off the top and the bottom surfaces of the thin film, and they have the interference, whether it is constructive or destructive interference. And let's look how it looks, like if we zoom and see what's happening inside of the thin film. So here you have 3 different mediums, N0, N1, and N2. And because it looks like N1 is thick and N2 is even thicker, so they are different densities. So every time the light reaches the first medium, N1, part of it is going to be reflected and part of it is going to go through. The one that is reflected is 180 degree shifted because medium 1 is thicker than medium 0. And the one that passes through is still in the same phase as the one that is coming. So this is in a certain phase shift, and when it's coming through the medium, so when it refracts, it's still in the same phase shift. So the one that is reflected is phase shifted, so it's not in the same as the green one. So it's 180 degree phase shifted because the other one is thicker. And then again, when it reaches the second medium, because second medium is also thicker than the first one, again this one is going to be 180 degrees shifted. So they're both 180 degrees shifted, but then it also depends on the thickness. I'm going to try to do my best to explain this thickness. So let's say if I have the wave that is coming in, something like this, and I'm going to separate them and do them straight if they are coming straight. Then when it is reflected from the bottom, it's going to be phase shifted, so it's going to be like that. I tried my best. Let me do it again here. So it's going to be like this. Okay. Now, what if I change my thickness? And what if I make this thickness not this way, but this way? Then when it reflects back, it's going to be, I'm going to give it a space. So it will not be this way, it will be, so this doesn't exist now. So this part does not exist. So when it reflects, it will be looking like this because it's phase shifted. So it's gonna go like this. But now this wave is in the same phase shift as the one that is coming. So they are in the same phase shift. So by changing this thickness, you can control whether this 180 degrees shifted ray is going to be 180 degrees shifted or not. So sometimes, because the different light waves are coming and passing through the mediums, you may see the red light, but you will not see the blue light because the distance between right here affects the shift. I know this concept is very difficult to understand. I did find a few videos for you, visual, where you can watch just the video where they show the wave travel, so you understand it better. And so you can make even both waves are shifted right now, but by adjusting the thickness D, so they give you right here D, by adjusting this D, you can make this 180 degrees shifted, and the other one also being shifted and coming out 0 degree shifted, even though it has to be coming shifted here and here. So when you have them happening like this, you have destructive interference. When they both have reflected in the same phase coming out, then it's called constructive interference. So if this happens, let's say for the red light, you will not see the red light, but because this thickness is good for, let's say, blue light, you will see the blue light coming, but not the red light coming. And this is where that beautiful image of rainbow on a thin film or oil on the water, that you can see a reflection of different lights because of this thin film interference. So let's say I have this picture and this distance is D. If this surface N3 and this is N2 and this is N1, and if I have N1 is less than N2, but N2 is less than N3, I will have two phase shifted. So I will have this one phase shifted and I will have this one phase shifted. So if the first one is phase shifted, the second one has to be half times longer than the previous one in order to be constructive interference. So the green one is the incoming ray. The red one is the first one phase shifted because it was reflected of the first denser medium N2. And the second one is going to be also reflected of the second medium. And what I have here is I have one full wavelength coming in. Let me do them in different colors. One full wavelength, two full wavelengths. So if I have two full wavelengths coming in, then when I reflect, I will have one full wavelength, two full wavelengths, and three. I get constructive interference. So if your D is the number of the wavelengths, so I'm going to say m times lambda, the number of the wavelengths, I'm going to get constructive interference in this case. So what I'm going to get is, if I have 2 times the distance there and back, so if this is the distance, and that distance is twice the distance there and then back, equals to number of the wavelengths. So I had 2 wavelengths in and 2 wavelengths out, so there's like 4 wavelengths. I'm gonna get constructive interference in this case. But if I had different case, if I had N1 is not as dense as N2, and N2 is denser than N3, maybe a glass, and the air and the angle is coming, the light is coming from the air into the glass, from the glass into the air. So this would be this case. And in this case, I could have the air, the water, the glass. So it's denser, denser, denser. And in this case, I have air, glass, air. So in this case, I would not have this second reflected light 180 degrees shifted, so I don't need to have m times lambda distance d. I don't have this distance to be twice, 3 times, 4 times, 5 times, that even number of wavelengths different. What I need here is, for constructive interference, is to make it the 2 times the distance is equal to m plus 1/2 of the wavelength longer to make it constructive interference. So in this case, I will have constructive interference. So it's really tricky. You have to understand it, you have to imagine it. If you can do one, just like I did the first one on the left side, the rest of them are easier because it's just the same pattern. And also, here, when you plug in lambda into the equation, that lambda is not the lambda of the wavelength in the vacuum. It's the one that is in that specific medium. So you have to always solve that lambda for that specific medium to use in the formula. I don't know about you, but I am not the memorization type of person. I don't memorize things. I have to see and understand them. And anything I memorize, I will not remember forever. But anything I understand, nobody can take it away from me, because even if I forget, I can sit down and figure it out. So what I just explained is in this box. If you have 2 times refracted case, that is, if you have N1 is less than N2 and N2 is less than N3, then you have this case. You have destructive interference when you have twice the distance, like as many the thickness. And then if you have constructive interference, you would use this formula. But if you had the case where N1 is less than N2, but N2 is greater than N3, then you would have only one time phase shift. Then your formulas shift. Then the top one becomes constructive, and the bottom one becomes destructive. So I don't get a chance to solve the question for you with a thin film in this video, but I will do it in the next one. So in the next video, we will get more practice on thin film interference. I will probably not go through derivation of the formula again. I'm just gonna use it. And thank you for watching this video, and I will see you in the next one.